Hi and hello all. Let us talk about electrophilic aromatic substitution reaction. This is a substitution reaction. Substitution, just like in any sports, like in cricket or football, one player comes in, other player goes out. In this case, one atom or a group of atoms adds to a substrate while some group or a group of atoms leaves from it. So that's substitution reaction, and it happens in an aromatic ring, and also it's electrophilic in nature, means the incoming group is an electrophile. As a matter of fact, outgoing group is also an electrophile. This hydrogen leaves as H plus from here, and in that place E plus comes in and stays as E. E plus represents the electrophile. Now what is an electrophile? Electrophile is something which allows electron or something which allows negative charge. So basically positively charged species or that's highly electron deficient species are electrophiles. Now aromatic rings have an extra stability. Aromaticity in itself is a special stability, right? Stability means unreactive. So to react with a stable species, we need a very reactive species. That's an this electrophile has to be very reactive. When you look at the stability, benzene, which is an aromatic compound, will not react with the bromine. Even though we represent it like it has 3 double bonds, it will not react with the bromine. The double bonds usually react with the bromine in this fashion. This particular type of reaction is called addition reaction. Bromine is getting added across that double bond. That is an addition reaction. So this type of addition reactions does not happen in aromatic ring. Instead, electrophilic aromatic substitution can happen. But for that to happen, bromine has to be activated. Usually, bromine is getting activated using AlCl3, the Lewis acid, or any other Lewis acid. So it's get coordinated with the aluminum. So let's check it out. We can show the lone pair in bromine. Draw a curved arrow like this. What does this mean? This means the 2 electrons from bromine is going to stay in between aluminum or aluminium and bromine. Let us color code this new bond. So the red colored new bond is a result of 2 electrons from bromine. Covalent bond in itself means 2 electrons in between 2 atoms. So the 2 electrons is from bromine. The maximum probability of finding these electrons is going to be in between bromine and aluminum. That means that is basically this bond. We can assume these electrons as point charges as far as organic chemistry mechanisms are concerned. Now, these covalent bonds consist of 2 electrons, and we can say one electron belongs to one particular atom and the other electron belongs to the other atom. Now both these electrons are coming from bromine, this particular bromine. Now one electron belongs to bromine, the other electron belongs to aluminum. That means this bromine lost one of its electrons, so it will have a positive charge, while the aluminum gained one of bromine's electron. Remember, these 2 electrons in this particular bond, one electron belongs to aluminum and one electron belongs to bromine, while both electrons belonged to bromine in the first place. So aluminum gained an electron, so aluminum will have a negative charge. Now bromine got activated. Now this is ready for electrophilic aromatic substitution. So let's consider this particular reaction where this activated bromine reacts with a benzene ring or an aromatic ring. The 2 electrons in this pi bond is going to stay in between this particular carbon and this bromine. We have to show it using a curved arrow. So pi bond is going to break, and that 2 electrons is going to stay in between this carbon and this bromine. That means a new bond is going to form between this carbon and this particular bromine. A new bond is forming to this bromine. An old bond can break. It will break in this fashion. The 2 electrons in this bond is going to stay on bromine now, this particular bromine now. We will have a situation, the pi bond is gone and we have this bromine attached there. This particular bond got broken away. So we have a situation like this. We added this hydrogen. It is there actually. This hydrogen is there anyway. So where is this hydrogen coming from? All these carbon atoms having a hydrogen, because benzene ring in itself is C6H6. All these carbon atoms are bonded to one hydrogen. That means, so this carbon, this carbon, this carbon, this carbon, this carbon, and this carbon. All of them are bonded to one particular hydrogen. That's the molecular formula is C6H6, benzene's molecular formula. For simplicity, we haven't shown that. Usually we don't show it. It's very obvious, that's why, but at this stage we need to show that hydrogen on that particular carbon. That's the new bond between this carbon and this bromine. So both electrons are coming from this particular pi bond and they are going to stay in between this carbon and this bromine, or the maximum probability of finding those electrons are going to be in between this carbon and this bromine. So that's the new bond. Now these 2 electrons belonged here, this pi bond, right? Now they are here, means When it was here, that's the old situation. This pi bond, consider this pi bond. One electron of that pi bond belong to this carbon and one electron belong to this carbon. Now both electrons are here. In this particular bond, one electron belongs to this carbon and one electron belongs to bromine. Now who lost an electron? This carbon lost an electron, right? Because earlier these two electrons were here and one electron belonged to this particular carbon and one electron to this carbon. Now both electrons are here now. Here, one electron belongs to bromine, one electron belongs to this carbon. That means this carbon lost one of its electrons, so it will have a positive charge. A neutral species losing an electron means it will have a positive charge. So let's add that positive charge. So we have a carbocation. This is an intermediate, a sigma complex. This is the famous intermediates in electrophilic aromatic substitution, this sigma complex. Now this can have resonance structures. Now let's go back to the reaction. So here, this is the intermediate. It has got 3 resonance structures. But anyway, this is not aromatic anymore. The extra stability, the special stability, so the species lost its extra stability or that special stability, aromaticity. So this is energetic and this will lose its energy and try to become stable, try to become aromatic. So re-aromatization is a common process in this type of reaction. The 2 electrons are going to stay in between this particular carbon and this carbon. That means there is going to be a new bond here. So that's written here. Now, once these 2 electrons are here, one electron belongs to this carbon, one electron belongs to this carbon. So this carbon got an extra electron. So it will have no positive charge. Positive charge plus an electron means neutral, right? So this will be neutral. So we have our bromine. We have our bromobenzene. In an overall picture, the hydrogen, this carbon got replaced by bromine. So all the carbons are equivalent in benzene. So any hydrogen can be replaced by bromine. And that's how it's a substitution reaction. And that's how it's an electrophilic aromatic substitution reaction. And that will be the general mechanism. And that will be the general mechanism of substitution reactions. There will be an electrophile. Most often, the electrophile has to be created because as it's very reactive. So this is just an example of electrophilic aromatic substitution. This bromination reaction is just an example. There are many electrophilic aromatic substitution reactions like nitration, like sulphonation, and Friedel-Crafts acylation, Friedel-Crafts alkylation, etc., etc. In all those reactions, an electrophile has to be prepared. Usually, electrophile is very reactive, so it has to be prepared in situ at the time of the reaction. And then that electrophile reacts with the aromatic ring and a sigma complex forms. And then that sigma complex re-aromatizes to form the product and the electrophilic aromatic substitution completes. And of course, in all these cases, this sigma complex will have this type of resonance structures. An electrophile can react with aromatic ring and form this particular substitution reaction, electrophilic aromatic substitution reaction, just like I have showed here with the example of bromine. So this could be NO2 plus, this could be CH3CO plus, anything like that. Thank you.